My name is Tadej, and here with me on stage is also Rok. We're both colleagues at GateHub, and today we will talk about GateHub Data API. Yeah, so first question, what is GateHub Data API? It's basically a drop-in replacement for Ripple Data API. And now the question, what is Ripple Data API, right? In very short sentence, it's API for getting analytical and reporting data about XRP Ledger. So, for example, you can get Ledger data, but you can argue that you can get Ledger data also by RPC call to the RippleD server, right? Yes, you can if you have Ledger index or hash of Ledger. But for me personally, I want to get Ledger that was closed at 1st of January in 2018 at 1:34 a.m. or something like that. Or I want to get transactions that happened between let's say last year, that were payment transactions that resulted in bad dry, and the issuer was GateHub, for example. So yeah, because it's drop-in replacement, it means that everybody who used Ripple Data API will just be able to, just change the domain, and it should work, right? The URL after the domain will be the same, the payload in the request will be the same, and the payload in the response should be the same. And yeah, we will support both, the single sidechain that there is. So we will support Zaho, we will support XRPL, and we will have support for both testnet and mainnet. And we decided that we will monetize it a little bit. So if you are working on some small projects, if you are a developer, you will be able to use it for free. If you do a lot of API calls, for example, per day, we will treat you as a power user, and you will need to pay something. I don't know how much. That's up for discussion. So yeah. And yeah, it's a big project. So both me and Rok were working on it for last year, a little bit more. And yeah, we of course encountered numerous challenges. The first one is to have robust infrastructure. And last year in October on Discord, I believe, somebody talked about how much is Ripple paying for their version of Ripple Data API, and the number was huge, very huge. I almost fell out of my chair, really. So yeah, we needed to bring that cost down. And you always need to talk about security, right? Even though the data on the blockchain is public, you want also the data that you calculated and saved in the database to be immutable, right? So on blockchain, it's immutable, but also in the database, it needs to be immutable. You cannot just change some data for the last year, because that would ruin everything, especially if you're using this data API for some accounting information. And we are talking about a few terabytes of data, and of course, you need to have fast and low latency queries, right? And the ledger synchronization should be on point, very quick, and reliable, right? And we went into some database that nobody knew about, anything about that database. So it was quite a learning curve to set up that database and optimize it for this kind of data. And both me and Rok are developers, and I don't know a single developer that likes to write API documentation. So we also need to write good API documentation. So I hope that we'll be able to do that. So let's break it down a little bit. So of course, always you have infrastructure, then we have database, we have client API service, and some service that we are calling it syncer for syncing the data and do some calculations. So if you start with infrastructure, GateHub is running everything in the cloud, in Google Cloud Platform. And for these kind of projects, we are leveraging Google Kubernetes Engine. Why? Just because we know how to use Kubernetes. It's easy to use for us. If there is some bottleneck in API, you can always spawn some new replicas of API. We also have in the infrastructure, we have RippleD, own RippleD instance, and own ZahoD instance. And yeah, for the database, we decided to go with ScyllaDB, and yeah, we are running ScyllaDB with 3 data nodes for the testnet. So let's go to the API service. So API service, we will support both gRPC requests and HTTP requests. So if you look on the left side, you have RESTful call. That's basically JSON through HTTP. That goes to reverse proxy, and reverse proxy will translate that to the gRPC. So that means that under the hood, everything is gRPC when it hits our service. So on the right side, you can see the example, right? I want to get ledger information with index 32,570. So the first one, that goes to reverse proxy, and it will translate it into the GateHub Data API.ledgers with this identifier. It will hit our gRPC service, and you will get the data. It's that simple. So I'll pass down the mic now to Rok.
So I'm going to talk about the second half of the platform. The first one is the mentioned syncer. It's a service that, as the name implies, it syncs the data that is flowing through the ledger, processes it, and persists it in a database. And one thing is, it must do so reliably. It must handle any downtime, any disconnects from the RPL, any server faults, any infrastructure faults, and it must pick itself up and backfill any missed ledger data. It's useful for it to be configurable, so any settings that are variable should be easily modifiable. For instance, again, the URL to the RPL, the number of workers, the type of chain, any specifics should be easily settable. We distinguish two runtime modes. The first one is the backfilling, so we have to process the already existing data or reprocess it if we require. And the other one is syncing the live data as it develops. So we subscribe to the ledgers, and once they get validated and broadcasted, our syncer picks it up and processes it. We design it to be modular service, so we have different modules. Each module does one thing and is independent. That makes it more testable, and we can switch out modules as required. One thing for us was, in the early stages, we tested different databases, and we just created another module with another database and plugged it in, and it runs in the same program. It has to be parallelizable, so we have to process multiple ledgers independently and in parallel, so we can process them more quickly. We did a quick test, so we have the so-called workers. What the worker does is fetch the ledger, the accompanying transactions, processes them, parses them, and inserts them into the database. And we did a quick test for 1,000 ledgers to see how much time it takes to process these ledgers. So one worker took about 10.5 minutes, 2 workers around half that time, and so on. So 10 workers took 1 minute and 10 seconds. So we could estimate it, how much time it would take to backfill all the ledgers that were already validated. So if you do some quick math, 90 million ledgers with 10 workers would take about 37 days. That's of course 73. Sorry, that's of course not accurate, but it's a rough estimation to see how much time we have to reserve. Next one is the database. So this is arguably the core of similar projects such as a data API. And the first decision is we have to pick a suitable database. Picking a database, the infrastructure depends on the choice of the database and the surrounding services. So we have to look up the data size and the scale of the data that we will be processing it. We have to plan the queries and the functional and non-functional requirements. As said, we want to be a replacement for the existing API, so we know what queries we want to support. Another important distinction is we have to pick either a relational, traditional database, a NoSQL database, time series, vector database, graph database. They all have their own strong points and weaknesses. We ultimately, we also come across the CAP theorem when deciding on the database. CAP stands for consistency, availability, and partition tolerance. And the theorem states that in a distributed system, you can only guarantee two out of these 3 points. We ultimately decided to go with ScyllaDB. It's supposed to be meant to be a fast NoSQL database that is scalable and fault tolerant. An interesting thing when working with Scylla is a derivative of Cassandra, if some of you know about it. It's interesting because when working with such a database, you have to think about the queries beforehand. It's a query-driven database, so you have to think about what you're going to use that database for, as opposed to creating models and relations and then go from there. When planning a database, it's useful to do some math to see how much data we're looking at. If we take just one transaction, we filled out a couple thousand transactions. We got an average on 430 bytes. And if we do some quick math, we have around 34 transactions on average per ledger. And if we have 90 million ledgers, for example, we're looking at 1.3 terabytes of raw data. This is only the transaction data, not any indexes or additional views. And if we take a step back and look at all other models to look at how much space is required for the whole database, we were looking at about half a gigabyte per 10,000 ledgers. This only includes transactions, accounts, balance changes, and ledgers. We will expand it to exchanges, more account data, escrows, and so on. This is just these 4 to get a feeling what numbers we are talking about. And we're looking at about 4.5 terabytes of data. And this does not include any replication. If we want to be more fault resistant, we have to scale up. So the main cost of such a project is definitely large storage space. We want to keep these costs down, so it's important to reduce the storage requirement and optimize the database as much as we possibly can. So we can look at some of the techniques we can utilize to optimize our database setup. One is to think about the data types that we are working with. For instance, if you have a numerical type, you have to think about how large the numbers will be to use the least number of bytes and bits for this column, let's say. And another example would be it's wasteful to save the date as a string, as you can just use an unset integer and save a lot of space. We will try to keep the table sizes small as it's possible. Smaller tables means faster queries, faster serialization, and of course, smaller size. Looking at specific transactions from the XRPL chain, we know that we have multiple transaction types. Each have their own set of data. And instead of dealing with different data, we can just serialize and encode the specific data and just save it as a blob in our database. We also want to minimize any redundant data, as naturally. But one example is it's wasteful to save tax success transaction status millions and millions of times. We can just use a numeric representations of these transaction statuses and also drive the cost down significantly. Partitioning sharding is used to chunk the data into smaller chunks, so across either one node or multiple nodes. that reduces query times and potentially increases our fault tolerance if we distribute it across multiple nodes. Since we are not using a relational database, we have to either normalize the data across multiple tables to facilitate these relations, or we can create small lookup tables which are used to quickly look up any related tables, which are also easily serializable. And important are also indexes and views. Both are used to optimize our queries, make them more dynamic, but these both come at a cost of storage space. So we have to balance our speed requirements and our storage options. So if you go back to the napkin math, we want to approximate everything before choosing a database and before investing into infrastructure. So we can calculate how much space we need. We can do this by thinking about the number of entities, tables, so in our case, transactions, ledgers, balance changes. All these objects have, we have to think about how many of these objects will be. And also, we have to think about the size of these objects. All that gives us a rough estimate of the size that we are looking at. Another metric is we have to think about the types of operations that we'll be conducting across our database. Will our service be read or write heavy? What will the queries be? And with all that, we can get a sense of the bandwidth and throughput that will be required to facilitate these needs. Calculating everything beforehand is all well, but it's useful to do a quick checkup of how our estimations hold up in real world. So we did a quick test. There's a chart which shows how much storage each entity takes. We did an analysis on transactions, ledgers, and balance changes to see how these storage requirements of each entity grows with the number of ledgers, which is our core entity. We did a pretty good job of estimating, for instance, transactions, but let's say balance changes, which are derived from the affected nodes, are more difficult to predict how these will scale up. So this is also a good test to see how everything scales with the number of data. So let me finish off with our quick roadmap. We are finishing the first and second step, so finishing the syncer, finishing the API, and after that, when everything is well, we want to backfill the ledger. That's going to take some time. We want to focus on API documentation and in the future support sidechains. So I think the takeaways regarding the planning is we're doing everything we can to think about the use cases, think about the requirements, because changing everything in the middle of the project is cost a lot of money, time, it's frustrating. So we did everything we could to put a good foothold for our services. And we wish to finish everything up and launch a beta for all developers. We want to incorporate it into our own project, and I hope we will have something to give you soon to give your feedback. Thanks.